Soils form and remain in the subsurface probably for thousands of years, gradually getting buried, sometimes being eroded, and new sedimentation comes on top. But in most cases, natural soils have been in place for a long, long time. That means that particles become closely in tune or connected with neighboring particles, and other processes may be taking place, like some form of diagenesis, which may involve cementation. Not always. Particles, for example, may creep and deform without creating bonds themselves. Imagine you take a lead shot and you squeeze it. It may not form bonds if there was a rust layer. Still, the soil will have some form of diagenesis due to deformation, which will manifest on properties. Today, I would like to explore the effect of cementation on soils. And to be clear, this happens both in coarse-grained sediments as well as in fine-grained sediments. But the case of fine-grained sediments is going to involve sharing divalent ions, for example, two particles connected by a calcium ion. There may be other forms of cementation as well. So instead of addressing that one, which you may want to go back and review double-layer theory, we are really going to have in our minds the model of the coarser grains, starting with the silts all the way to the sands and gravels. So the first thing that we need to identify is how does this cementation grow in the pores. And so let's call that the pore habit of cementation. Well, one possibility is that if you have grains, all of a sudden, excess reactants will reach to a point that will form a precipitate. However, this is very unlikely that it will precipitate in the middle of nowhere. This is called homogeneous nucleation. In fact, you know from your own experience that if you have a glass with a carbonated drink like Coca-Cola and you sprinkle salt, you will see gas coming out very fast because you have added a nucleation site where bubbles can come out of solution and gas can come out of solution forming these bubbles. And the same will happen with boiling and also with crystal precipitation. And so most likely what we are going to have is that we will find grains and precipitates nucleating on the surface of grains. So this is heterogeneous nucleation. This is a crystal here growing. Now there are other possibilities, like for example, we could have the grains and for some reason a layer of cement forms around the grains. This is a coating approach. Now in other cases, which I'm sure you can anticipate, there could be grains and driven by unsaturation, most likely, cement forms between the two contacts, just at the contact. Finally, once a crystal forms, it likes to grow. So instead of more crystal nucleating on new surfaces, on the mineral surface, it likes to grow on top of an existing crystal of its own kind, because the structure is already set for new atoms to position themselves in the right location for the crystal to grow. And so there is a tendency for ripening. In other words, the larger crystals will grow at the expense of the smaller crystals, and cementation may try to come together, resulting in patchy saturation. So let me show you the case, whereby a group of particles experiences high cementation while the rest is still uncemented. So to summarize, this would be homogeneous nucleation. This is heterogeneous. This is coating, almost like pendular regime in unsaturated soils, so we call this pendular, and this patchy. We have identified all these forms of nucleation of cement in soils, with the exception that this is quite unlikely from a probabilistic point of view. Now we can begin to think, how are these going to affect the macro scale properties? And we're looking for the asymptotes of the mechanical behavior, in other words, the smallest strain and the largest strain. And when we look at the largest strain, we have to be thinking at the end condition, at the asymptotic conditions, kind of the critical state conditions, but also the transition, the dilation to get to that point. And we also want to see the impact on fluid flow. So let's start with the effect of cementation on small strain stiffness. If the soil is uncemented and we squeeze the soil, small strain, we are not causing fabric changes. I invite you to review one of the earlier videos on small strain behavior. So it's constant fabric, and we squeeze it, then all the deformation that takes place of the skeleton is actually due to contact deformation. So the small strain stiffness is going to be very sensitive to the size of the contact, and we predicted that from Hertz's theory. And so if we plot stiffness, and we are typically going to measure this stiffness using shear wave velocity to avoid the effects of water stiffness. So we just look at the stiffness of the skeleton. So let's say that I'm going to plot the shear wave velocity versus the effective stress that is confined. And by the way, I'm going to plot this in log-log scale because these are power equations, as you may remember from Hertz's theory. And so in log-log scale, these are going to become straight lines. If the soil is uncemented, this is the behavior. And this slope here is what we call beta. The intercept, in this case, is logarithmic, so it doesn't go to 0, it goes to wherever. That intercept would have been at the effective stress of 1, this becomes 0. So this intercept is what we call alpha. For uncemented soils, coarser soils, this beta, in terms of shear wave velocity and stiffness, is in the order of 1/6 to 1/4. It's in that range, 0.16 to 0.25. Now, if the soil is cemented, imagine that you have a cementation that is like a pendular regime there at the contact. Now the contact is not deformable anymore. So a cemented soil has a surprisingly flat stiffness with respect to the state of stress at low confinement. So this is the behavior of a cemented soil, insensitive to the state of stress until it reaches a fairly high stress where it joins the stiffness of the uncemented soil. And you can imagine why that happens, because if you had an uncemented soil and you squeeze it, eventually the contacts become flatter and flatter, and that becomes equivalent to the flatness of the contact with cement. And that is where the two lines merge. Now, we can begin to realize that the higher the cementation, the higher this line is. So we can say that this is the mass of cement over the mass of mineral. But you can also realize that much of the cement in the coating mode is not contributing to stiffness, because all the cement that is anywhere in between the grains is not contributing to stiffness. Therefore, this system is less efficient affecting stiffness per mass of cement over the mass of mineral than this system where all the cement goes to the contact. And so not only the mass of cement over the mass of the mineral, but also the pore habit will determine where that line goes. And just for the following the previous analogy, if this is pendular cementation, this will be very effective. If it is coating cementation, it will be less effective, as you can see, for the same amount of mass of cement. So clearly two parameters emerge, which is the relative amount of cement with respect to the mass of the minerals, of the original particles themselves, and the pore habit are very important to this behavior. Now let's consider a few other examples. For example, the case of we have a loose soil, almost like a loess, a loose soil that we're going to begin loading. At the beginning, it has cementation. So this is the actual evolution of the soil. It went in following this line, which is the uncemented soil. It went in until the burial depth. At this point, it gets cemented. It goes up, and this is the effect of cementation. So this is step 1, burial. Step 2, cementation. And now let's say that we are going to continue loading the soil. If we continue loading the soil, it will follow the horizontal line like this one until it merges to the uncemented soil. But if the soil is very loose, it may give us this type of behavior. This is collapse due to loading. The cementation at contacts breaks down and the soil falls onto the uncemented line. And then it continues along the uncemented line. This happens whenever there is some cementation in loose soils, and I'm going to put references at the end of this presentation so you can find evidence of this. And it is very likely that this type of behavior is responsible for some of the failures we see in tailing dams or fly ash storage ponds, where there is early diagenesis, and then upon further loading, that light cementation breaks down. That collapse may create very high pore pressures, leading to the failure of these storage systems. The other example that I would like to highlight is that, once again, these are all in log-log scale, so I can use the linearity for that purpose. So let's explore the effect of sampling. Initially, the soil got buried. At this point, it gets cemented. And let's say that we take the soil with a perfect box type of sampler, but that soil is going to experience unloading. And so imagine that the cement at the contacts, first of all, the contacts got squeezed. So this is a loaded spring. Now the spring is squeezed there at the contact. Now the cement at the contact during unloading gets stretched, and the cement actually breaks in tension. So this occurs during unloading. I decrease the load. The shear wave velocity at the beginning doesn't change much, but eventually these tensile forces at contacts break the cement. And then I bring it to the laboratory and I squeeze it again to bring it to the state of stress in the field, but the sediment never recovers the original stiffness, and in fact, it goes asymptotically towards the unstressed sediment. So to summarize, this was burial, this was cementation, this is step 3 is unloading due to sampling. Step 4 here is when I reload in the lab, I never recover the stiffness. For this reason, it is very important that we measure the shear stiffness in situ, and shear wave velocity is probably our best possibility to do so. To summarize, we see that both pore habit and the relative mass of cement with respect to the mass of minerals determine the shear stiffness of our sediments. Clearly, the pendular regime is the most effective from the point of view of the amount of cement that is localized at the contacts, but both of them are very effective on stiffness. Both of them. There is a transition stress where it is cementation control and it becomes thereafter stress controlled. And we saw that there are some implications of this cementation in light loose sediments. Underloading, they may experience collapse. We have observed it, may be responsible for the failure of dams, and also the effect of sampling, which by unloading, it permanently breaks the cementation. We do not recover by reloading in the lab. Now let's explore the other asymptote, the soil behavior at large strains. And the first observation comes from the stress-strain behavior. So let's run a typical triaxial test where we plot the deviatoric stress versus the vertical strain, and here the evolution of void ratio versus vertical strain. If the soil is a contractive soil, the uncemented soil is contractive, then this behavior is going to be strain hardening. The more we deform it, the denser it becomes, so the void ratio decreases, and the density becomes, there are more interparticle contacts, the strength of the soil becomes increases, becomes higher with the deformation, but it goes to an asymptotic behavior. Now, if there was some cementation, we may see that the soil is going to go to a peak response, and then the cement begins breaking, and then it goes to another asymptote. And this is now the product. It was the soil at the same initial density, but this is the product of cementation. And so, in fact, the soil also may have tried to contract a little bit, but then eventually it picks up the effect of cementation and it goes way up. And this component here, which is what we call the dilation, a measure of dilation, can be very pronounced. And you may wonder why. Well, think of a soil as an arrangement of particles, and we're going to draw here some arrangement. And during shear, what happens is that it breaks like in blocks. So let's say that this is a block of particles that is going to break together, and this is another block. And so it is like having cubical particles that are breaking relative to each other. Now, these cubical particles are very dilated because, as you can imagine, they have to climb one over the other. So even though the original soil was contractive, the cemented soil may behave quite dilated because of the blockiness of the structure as the soil breaks down. Now, at very large strains, we're going to destructure all this, and we may still have some residual effect of the excess amount of mass due to the cementation filling the voids, but this is a good metaphor to get started. The next question is, will there be differences whether there were different pore habits in the cementation process? So now let's summarize the previous results in the form of the QPE diagram. I'm going to show you the two projections, and instead of flipping it over, here I plot E versus P prime. And let's explore two different cases, one for heterogeneous nucleation. In other words, particles have formed crystals on top of their surface, which is going to increase surface roughness. And for this particle to move, it will have to dilate, of course. And also notice that you can do very simple geometric analysis to see how much mass you need for a crystal growing pore structure to actually touch another pore with some statistical assumptions. And probably you will need about 10–15% of the volume of the pore to be occupied by the cement. So this requires quite a lot of cementation, but if we do that, in the QP space, this would be the slope of the more Coulomb curve, now in QP, for the uncemented soils. And as we add cementation, this is going to move the lines up. So this is when I increase the mass of cement with respect to the mass of minerals. In the EP prime, and please notice that I have void ratio moving up, this would be also a shift upwards due to the fact that we have cementation with significant dilation. So this is the case, the one I'm showing here, for heterogeneous nucleation. Now let's explore the case for patchy saturation. And patchy saturation has a different effect. Notice that during shear, a failure plane will probably avoid the patch, which is very strong, and so the failure plane will go around the patch, which demands more energy to shear, but it's still a very frictional system. And so in the QP space, if this is the uncemented soil, we see an increase in friction angle due to the mass of cement with respect to the mass of the mineral. And the effect translates in EP prime as similar lines probably converging at very high P prime, which is probably the case for all these situations. This has been explored with discrete element methods for fairly constrained geometry, so it deserves further analysis. But there is a take-home message. As we increase cementation, we may increase this effect of cohesion at the intercept, but we may also cause increasing friction because of the tortuosity of the shear plane. And in both cases, there will be increasing dilation, so there is a shift in the critical state line towards higher void ratios. The other parameter that cementation affects is permeability. And we can go back to permeability being understood from a parallel tubes, the Hagen-Poiseuille equation. And then we made it more complex with Pore network models, where we put lots of tubes interconnecting each other, and we use the Hagen-Poiseuille for each segment, but the Pore network understood the whole evolution of permeability. Once again, those are good videos to review. But if we take the Hagen-Poiseuille equation, as you may remember, the flow rate is proportional to the radius of the tube to the fourth, and the gradient and the viscosity of the fluid. But this is the important one that I want to highlight, the tube radius. So if we had a tube and all of a sudden cement begins growing in, now the effect on permeability is quite dramatic. And you can estimate it once again, and you can put it in your Pore network models. You can simulate patchy saturation or any coating saturation, any one of those mechanisms that you envision, to see what is the effect on your permeability, on the permeability of this system where cementation is taking place. To summarize, cementation affects all our properties. It has primarily a very strong effect on small strain stiffness. Gradually, cementation will begin breaking down, but still has a very important effect on the large strain properties. In particularly, dilation, as the system is beginning to break down because of the blockiness of the cemented structure as it evolves towards failure conditions. Two important parameters is not only the amount of cementation, but how did the cementation form within the pores, the pore habit. Most likely, it started as heterogeneous nucleation. But if there were biofilms coating the particle, it is very likely that it may have formed a coating surface around each particle. If it formed under unsaturated conditions, as the soil began drying and all the species were concentrated at the contact where precipitation took place, it's going to be a pendular type of cementation, which is the most impactful. And because of Oswald ripening, it may tend to evolve towards a patchy structure. It affects small strain, dilation, therefore the evolution towards a critical asymptotic state, both in the terms of strength and in terms of void ratio versus confinement, and as well as permeability. Cementation is best detected in the field using shear wave velocity. Don't miss it. It can really affect the design.